This warm-up says, write an equivalent fraction with the largest possible unit. Essentially, what they're looking for you to do is simplify or reduce these fractions. I see here in number 5 that these are both multiples of 9. So I can split it up. 9 fits into 72 8 times, and 9 fits into 45 5 times. 27 and 40. I know 27 is 3 times 9. 40 I could do 4 times 10 or 2 times 20, but there are no common factors, so 27 40ths is as simplified as it can get. You do not have to change these to mixed numbers. You can leave them as improper fractions. You might notice that there are other factors, but you are trying to get them in the most simplified format. You should be completing these in your composition book. Pause here to give yourself enough time to finish these. In this slide, we're looking for some things that you notice or maybe what you wonder. One thing that I notice, all of the evens have circles. 2, 4, 6, 8, 10, 12, 14, 16, and 18 all have a red circle. What's another thing that you notice? I wonder why they skipped the number 1. What's something that you wonder? We're going to move on to working in our workbook, and we'll come back to that photo later. Number 1. What is the side length of the largest square that can tile a 20 unit by 24 unit rectangle? Think back to our digital lesson. We're trying to make squares that fit perfectly into a 20 by 24 rectangle. I'm going to split up the factors of 20 and 24. And I'm just going to create a little table. I know that 20 is 1 times 20. I know I can multiply 2 by 10. 3 times 6 is 18, and 3 times 7 is 21, but there are no factors for 3 to make 20. 4 times 5 makes 20. The next number would be 5, but I've already used that. If 3 doesn't work, 6 won't work. 7 won't work. 8 wouldn't work. So those are all of my factors of 20. Now let's do 24. 1 times 24. 2 times 12. 3 times 8. 4 times 6. 5 wouldn't work because it doesn't end in a 5 or a 0. 6 is already used. 7 times 3 is 21. 7 times 4 is 28, so no 7 works. 10 won't work because it doesn't end in a 0. So these are all of the factors of 24. Now I'm going to go through and I'm going to highlight the common factors. We are looking for the greatest common factor, meaning the biggest one. The biggest number they have in common is 4. So the side length of the largest square that will fit into a 20 by 24 rectangle is a 4-unit square. This isn't a perfect sketch, but you would fit 6 4s across the width and 5 4s across the length. What is the greatest common factor of 36 and 48? I'm going to teach you how to use what's called a factor tree. So we're going to start by making a tree-style diagram. 36 can be broken down into 9 times 4. 9 can be broken down into 3 times 3. And 4 can be broken down into 2 times 2. I'm going to just use the ends of the branch. So 9 is not considered the end of a branch because it continues to branch out. So I'm looking at the ends. Again, 4 is not the end because it branches out from there. Now we'll do the same for 48. 48 is 12 times 4. 12 can be split into 6 times 2. 4 can be split into 2 times 2. And 6 can be split into 3 times 2. Now, we're not going to use ones because 1 is not considered a prime factor. So anything besides ones, otherwise we could continue to split this off forever. So now I'm looking at what they have in common. They have a 2 in common. So I'm going to write down the 2 that they share. They have a 3 in common. So I will write down the 3. They have another 2 in common. So we will write down that 2 as well. This has 2 additional 2's, and this has a 3, but there are no other factors that they share. To find their greatest common factor, we are going to multiply the numbers that were in both lists. 2 times 3 is 6. 6 times 2 is 12. So the greatest common factor here is 12. Now you could also do this in that table style. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. And for 48, we'd have 1 and 48, 2 and 24, 3 and 16, 4 and 12, 5 wouldn't work, 6 and 8, 7 wouldn't work, 8's already there, 9 doesn't work. And then we can go through and highlight all the ones they share. And then the greatest is 12. But the problem that I run into with this style is that sometimes we forget that there are other factors. And so we would skip one, or we would forget about one, and then we would miss possibly the greatest common factor. So I prefer the tree diagram, and that's what I'm going to continue to use. But if this style works better for you, feel free to use that. Here we're looking at 36 and 55. Last time I split 36 into 9 times 4, and I ended up with 2 3's and 2 2's. Let's try a different separation for 36 this time and see if we end up with the same prime factors. How about 3 and 12. 3 times 12 makes 36. 12 could be 3 times 4, and 4 is made up of 2 times 2. Again, I still end up with a 3 at the end, a 3 at the end, and 2 2's. So I still end up with the same prime factorization. 12 is not the end of a branch because it splits off from there. 4 is not considered the end of the branch because it continues to split off as well. 55. Well, I know it's a multiple of 5 because it ends in a 5. And 5 times 11 makes 55. Are there two whole numbers I could multiply together to get 5? No. How about 11? No, 11 is also prime. So now we're going to look, are there any prime factors they have in common? I have 5 and 11 here. Are there a 5 or 11 here? No. So the greatest common factor between these, if they don't have anything in common, 1 always is a factor of both. So the greatest common factor in this case is 55, or of 55 and 36 is 1. Riley has 28 pens and 14 notepads. She uses all of the pens and notepads to make identical gift bags for her teachers. What is the greatest number of identical gift bags Riley can make? Now that word greatest clues us in that we're looking for the greatest common factor. I'm splitting 28 and 14 into a tree, a factor tree. I know this is 4 times 7. 7 is prime, but 4 can be split into 2 times 2. 14 is 7 times 2. So here we have our branch ends. And they both have a 7 and they both have a 2. Seven times 2 is 14. So the number of identical gift bags Riley can make is 14. How many pins does each gift bag have? So if we're making 14 gift bags, 28 split into 14 bags leaves us with 2 pins for each gift bag, and 14 notepads divided by the 14 bags is 1 notepad. So here's that picture again. When we were doing the prime tree diagrams, the prime factor tree diagrams, the primes were 2, 3, 5. We saw 7 when we split up 14 and 28. 11 showed up when we split up 55. So what do you notice about the prime factors? These all have 1 shape around them. So this would be a prime factor, and so would 17. All of the prime factors only have 1 shape around them. The other type of numbers that have multiple shapes around them are called composite numbers. So we have primes and composite numbers. 14 is an example of a composite number. And we see here that it's made up of a 2 with the circle shape and a 7 with the pentagon shape. So it is a composite number. Here I see 15 has a diamond, so it has a prime factor of 5, and it has a square, so it has a prime factor of 3, right? 3 times 5 makes 15. So there's that example. 14 can be 1 times 14 or 2 times 7, so this is composite. But prime numbers can only be made up of 1 times itself, so 1 times 3. There are no other factors besides 1 and 3 that would work, so these would be an example of primes. Composite can be broken down into other factors. Primes are just 1 in itself. "28 has 2 times 14, 4 times 7, and 1 times 28. But are any of these considered the prime factorization? No, because 14 is still a composite number, and 4 is still a composite number, so we would have to split it up. 2 times, and then what makes 14? Well, 7 times 2 makes 14. So this would be the prime factorization. If we looked at this one, 4 can be split up into 2 times 2, and 7 is already a prime number. So this is also the prime factorization. Notice I have 2 2's and 1 7. The prime factorization is the same, it's just in a different order, but it still has the same prime factors. So it says complete the table for the number 36. If we were doing this in class together, you would be split up into teams, and each team would have a different factorization for 36, and then they would arrive at the prime factorization. We're going to do this together on the video. So one possible combination to get 36 is 2 times 18. Another is 3 times 12. We also have 4 times 9 and 6 times 6. Now to prime factors, the 2 is a prime factor, but 18 could be broken down into 9 times 2, but 9 is still a composite number, so we need to break that down even further, and 9 can be rewritten as 3 times 3. In this case, 3 is a prime factor, but 12 needs to be broken down. 12 can be split into 4 times 3, and 4 is also composite, so we can break that down into 2 times 2. Notice we have 2 2's and 2 3's in both of these expressions. Neither 4 or 9 are prime, so we're going to split both of those up. 4 is 2 times 2, and 9 is 3 times 3. Same thing with 6. 6 and 6 are not prime, so we're going to split those up into 2 times 3 and 2 times 3. In all 4 of these, we see 2 2's and 2 3's. For 48, we are also going to start with some given factors, but they will be composites. 2 is prime, but 24 can be split into 4 times 6. 4 can be split into 2 times 2. And 6 can be split into 2 times 3. So I have 1, 2, 3, 4 2's, and a 3. 3 is prime. 16 can be split into 4 times 4, but 4 can be split up into 2 times 2, and 4 can be split into 2 times 2. So again, we have 4 2's and 1 3. 4 isn't prime. It can be split into 2 times 2. 6 is not prime, or 12 is not prime either, but it can be split into 6 times 2. And we can split 6 further into 3 times 2. You see again, 1, 2, 3, 4 2s, and 1 3. 6 can be split into 3 times 2, and 8 can be split into 4 times 2, but we can split that 4 up as well into 2 times 2. So 1, 2, 3, 4 2s, and a 3. So here are the prime factorizations for both. And now we will highlight all the ones they have in common. They both have 2 sets of 2 and 1 3. To find their greatest common factor, we're going to write down 1 2, 2 2s, and 1 3. 2 times 2 is 4. 4 times 3 is 12. So this is just another way to represent all of those prime factors that we would get out of the tree diagram, just in a list format. Again, I still prefer the tree, but if you prefer this style, that's okay too. Just find one method out of the 3 that works for you and stick with it. So we're looking for the greatest common factor of 26 and 39. 26 is even, so it can be split into 2 and 13. 13 is prime. 39, I notice it can be 3 times 13, and both of those are prime. They both have a 13 in common, so the greatest common factor of 26 and 39 is 13. 13 is just 13 and 1, so it can't be split up. 14 can be split into 2 times 7, but there are no common factors between 13, 2, and 7. So when there aren't any factors in common, we use the only one that works for everything, which is 1. 1 fits into 13, and 1 fits into 14. Here we have a bit of a word problem using the greatest common factor. It says a group of 18 sixth graders and 24 fifth graders play a trivia game. Each is placed on a team. Each team must have the same ratio of the number of sixth graders to the number of fifth graders. What is the greatest number of teams that can play the trivia game? Again, there's that word greatest, cluing us in that we are looking for a greatest common factor. 18 can be split into 6 times 3, and 6 can be split into 2 times 3. 24 can be split into 4 times 6. 4 can be split into 2 times 2, and 6 can be split into 3 times 2. So the ones that they have in common, they both have a 2, they both have a 3, but 24 does not have another 3, and 18 doesn't have any more 2s. So the greatest common factor is going to be 2 times 3, the green times the blue, which is 6. So the greatest number of teams they can have is 6 teams. But part B asks how many go on the team. How many does each team have? If we are splitting the sixth graders up into 6 teams, that gives us 3 sixth graders per team. And the 24 fifth graders split on the 6 teams would give us 4 fifth graders. So there are 3 sixth graders and 4 fifth graders. On each team. You could also look at what remains. 2 times 2 is 4, and this one has a 3 remaining. Make sure your warm-up is finished in your composition book and your workbook is filled in for this lesson. If you have any additional time, you can work on your 6NS4 Check Your Understanding questions found in Google Classroom.